Okay, so just a few words about the units. So I'm going to go through your formula sheet and just point out what the units should be. So whenever you see B, this is sometimes called the magnetic field strength, but also sometimes called the flux density. So if you ever see the words flux density, then that's B. And the unit is Tesla. So B is in Tesla, T. Now this is I, and the unit for that is amps or amperes, and R is the distance. It's not the radius, it's the distance, and that's in meters. Same with this I here. N has no units. N is just the number of turns in the solenoid. Okay, F is the magnetic force, so that's going to be in newtons. L is going to be in meters because it's the length. Q is a charge, so that's going to be in coulombs. And this small v is velocity. Sometimes you'll hear it described as speed, the speed of motion of an electron, but it's basically the velocity. You're going to use the magnitude, so it is actually speed, in meters per second. Now phi is B multiplied by A, and that's called the flux. So when you see the word magnetic flux or just flux, that's phi, and the unit for phi is either Weber or Tesla per meter squared. So this has two units, not per meter squared, sorry, Tesla meter squared. But this is the proper unit for it. N, again, is just number of turns. E is an EMF, and EMF is always in volts. Okay, delta T in seconds, and delta phi, obviously that's just in Webers. Now, when you see the small letter E here, that's just the charge of an electron, so that'll have the same charge as Q. V is the same as that. M is in kilograms. Whenever you see mass, that should be in kilograms. This uppercase V here, this V over D, that's your electric field. So V is your potential difference in volts. That's not the same as little v. This is meter per second. This is speed, and this is potential difference. This is when you have two electric plates. Okay, when you study thermal physics, whenever you see Q, that should be in joules. Whenever you see P, that should be in watts. Whenever you see time, that should be in seconds. Whenever you see M, that should be in kilograms. This is not I, this is L. So this is the latent heat of fusion, or the latent heat of vaporization. For conduction, this is your change in temperature, so it should be in Kelvin, but because it's a change, it can be in Celsius as well. T, always in seconds, and this L, it's not the length, it's the distance between the hot end and the cold end. So if you've got one end that's hot, and one end that's cold, then T2 minus T1, or T hot minus T cold, that's your delta T. And this is, your L. A is the area, the cross-sectional area in meters squared. So that's that area. You may need a little formula for the area. If it's a circle, your area will be pi r squared. If it's a rectangle, then the area will just be the length times the width. Okay, but this length obviously is not the same as that length, right? This A will have the same unit as this A. This T, this time has to be in Kelvin. It can't be in Celsius. So delta T we can have in Kelvin or Celsius, but T has to be in Kelvin. Okay, E is emissivity. I think that's unitless, and that is a constant that's given to you. All right, and P is the power, and that's in watts. Now, in thermodynamics, P is not in watts. P this time is pressure, and pressure is normally in pascals. Sometimes, if you have only P and V or only P and T, you can use other units. So we can say that if it's isothermal and T is constant, you can say P1 V1 equals P2 V2. This is if it's isothermal. That means T constant. If it's adiabatic, you have this, and gamma here. This is called gamma. In some questions, they'll just call it gamma, and it has no units. Okay, you might also need to know that if volume is constant, then P1 over T1 equals P2 over T2, and T is always in Kelvin. And P, it doesn't matter what unit, as long as they're the same unit. It doesn't matter what P is in this equation and this equation. Okay, the final equation that can come out of this is if the pressure is constant, we can say V1 over T1 equals V2 over T2. I think this is called Charles' law. And again, T has to be in Kelvin, and V is in meter cubed. All right, so if you have centimeter cubed and you need to convert to meter cubed, then you multiply times 10 to the minus 2 cubed. That means multiplying times 10 to the minus 6. Okay, U is in joules, Q is in joules, delta U is in joules, and W is in joules. W is in joules. P is in pascals, and V is in meter cubed. For these equations, again, W and QH are in joules. E is unitless, but sometimes we multiply by 100 and put a percentage sign. Now, the same goes for Q, hot reservoir, cold reservoir, hot reservoir. Joules, joules, joules. But here, you've got temperature. So each of these temperatures is in Kelvin. So Kelvin, Kelvin, Kelvin. Okay, make sure you don't use Celsius here. It has to be Kelvin. Okay, so that's all about the units. I don't think there's much else, except simple harmonic motion. Let me see if we skip that. Yeah, so simple harmonic motion, you need to know things like acceleration is in meter per second squared, x is in meters, omega is in radians per second. M is in kilograms, T is in seconds, F is in newtons, L, length, is in meters, K, the spring constant, is in newtons per meter, L is in meters, G is in meters per second squared, T is in seconds. Not sure about the constant mu, but it's a constant, it should be given. V is in meter per second. T is the same as this. And S here is in meters, it's arc length. I think they should have given you S. There's a formula for S. S equals L theta for small values of theta. So theta needs to be very small. So we're talking about 0.1, 0.2 radians, very small values for theta.